Okay, so inorganic chemistry, transition metals, trends, ligands, and geometries. As I said, this is kind of an overview or introduction to some of the topics that will be encountered in more detail, I guess, in other parts of the course. So what is a transition metal element? So elements with valence D or F electrons are typically classified as transition metal elements. So the ones that we'll be predominantly encountering will be the D block, but of course, lanthanides in the F block are also transition elements, and they have somewhat similar chemistry, although generally not everything that applies to the D block applies to the F block and vice versa. More precisely, we can consider any element that has a partly filled D orbital in its most common oxidation state. So generally, if it's in its most common oxidation state and it has a full D orbital set, then it's kind of not really going to behave as we would expect a transition metal to behave. So for example, zinc, depending on its oxidation state, can either be similar to a transition metal or not. And so what makes transition metals special? Well, unlike, for example, S block and the P block, which are typically going to be locked into one particular oxidation state. You know, for example, lithium, it's typically +1, for magnesium +2. Things like nitrogen usually is nitride, fluorine, for example, is fluoride and whatnot. Transition metals are not restricted in such a way. Usually there are many different accessible oxidation states, so many of them do happen to be around the sort of +2 to +4 oxidation state range, but it's possible to have other oxidation states, all the way up to, like, for example, +7, +8 for different metals. They have variable coordination numbers. So as we saw in like our treatment of VSEPR theory and trying to understand the compounds of the P block, we would have seen that most elements typically adopt a certain geometry for their compounds. In transition metals, that's not necessarily, it's not, again, not necessarily locked in. I suppose one of the major benefits of a transition metal, I guess, is that it's able to just be flexible in that way around how its morphology is, how it coordinates, and it's that flexibility which we will see later on in its reactions, which sort of enable it to be used in a catalytic manner, so it can like increase its coordination number or decrease its coordination number as the situation requires. They're also typically colored compounds, so whereas most S and P block compounds are generally colorless, some of them do have a color. By and large, like compounds of carbon are mostly colorless, except for maybe some of the polyaromatics. But transition metals are often, complexes are often colored, and they often exhibit paramagnetism. So what are the applications of transition metals? So there are many. Some of them are, like, for example, in metallurgy, in catalysis, as I've mentioned, biochemistry. So iron complexes form an important part of hemoglobin in the body. Magnesium then in plants as well is a very important, well, magnesium is not really a transition metal in that instance. And then medicine, like you've got one of the most common anti-cancer treatments is cisplatin, with a platinum transition metal complex. So a little bit of overview for the D block elements. So the first series goes from scandium to zinc. We have about 10 elements, and we're filling in the 3D orbital. And the second series goes from yttrium to cadmium, which is 10 elements again, filling in the 4D orbitals. The third series then is lanthanum to mercury, 10 elements again, filling in the 5D orbitals. So there are 10 elements across in the D block. There are 5 D orbitals. At most, we can have 10 D electrons, and so we have 10 elements in our D block. Lanthanum then, the lanthanides are F block elements, so they have F orbitals in their valence, which we have 7 F orbitals. So we have 14 elements. So the lanthanides in the F block go from cerium to lutetium, which is 14 elements filling the 4F, and then these all have similar chemistry to lanthanum, which is dominated by the 3+ oxidation state. And then the actinides are thorium to lawrencium, which is 14 elements, filling the 5 f orbitals. As it says here, this lecture is concerned with the chemistry of D block elements, especially those of the first transition series. So typically just the first row, but apart from the platinum group, which we'll probably encounter in organometallic, the second and third typically have somewhat but yes, you are expected to be able to understand that there may be differences between them and that there may also be similarities. Generally, I'll point those out, but of course you can get that from the topic videos and also from the textbook. So here is how the general sort of valence electron configuration goes for these first row. The third row of the periodic table will be the first row of the transition metal elements. So fourth row of the periodic table, so scandium is the 4s2 3b1, forms a 3d3 complex whenever it's in the complex form. So the neutral gas phase typically fills the 4s first, as we would understand from our electron filling rules, the Aufbau principle, and so on. But then whenever it forms a complex, typically the s electrons are shifted across into the d orbitals, because the d orbitals are, which will be more apparent to you as we go through and we try to understand how some of these complexes actually form. So the complexes of d block elements, we consider the electrons to be in the d orbitals. Typically, that's where they're most exciting. D electrons is therefore important to define the element's behavior. So oxidation states, so removal of electrons through oxidation generates cations. So that's pretty standard stuff. The number of electrons removed from the neutrally charged one oxidation state, remove 2, you've got the +2 oxidation state. The interesting thing about transition metals are those in the D and F blocks is that they can have variable or various different oxidation states. They're not sort of confined to one particular oxidation state because ionization energies. And so this needs to be included in the d electron count. Typically, the ionization energies are pretty similar for several different oxidation states, which makes it quite accessible. So for example, iron 2+ is therefore going to be D8, -2 makes it D6. So there's 6 d electrons. Starts off as D8 in the atomic form. In the complex, then it's got a +2 oxidation state. So we've removed 2 electrons, gives us a D6. So a transition metal is an element that has a partly filled d or f orbital in its typical oxidation state. So obviously 6 electrons is not 10 electrons, which we would need to fill the d orbitals. And these 6 electrons mean that we have a partially filled d orbital set, and we therefore have transition metal by definition. So here are some common oxidation states for the first row of the transition metal series, the D block. You're not really, you don't need to memorize, for example, that chromium has a very common +6 oxidation state, although actually that's not a very good example because chromium is quite famous for its +6 oxidation state. But anyway, so most of them have a favorable 2+ or 3+. So for example, you can see here there's a lot of 2+ that are highlighted and 3+ which are also highlighted as being common oxidation states. That's what the yellow boxes mean. The other ones are available and are possible, but are less commonly observed. But you can see it can go all the way up to +7, for example, in the case of manganese, which is the ion in permanganate. So some d electron counts. So we have here the oxidation state. So these are the kind of the common oxidation states again, and then the number of electrons that those correspond to. So typically we find that removing most of the electrons or removing half of the electrons generates the most common oxidation state. So scandium transition elements, so they have partially filled d orbitals just without needing to lose any electrons. Scandium, yttrium, and lanthanum only form salts with 3+ oxidation state, which is D0. So here, scandium typically forms the 3+ oxidation state. They behave more like S and P block metals. Copper 2+ is D9, forming green-blue colored species, and this is transition metal. So, for example, copper sulfate, quite a famous blue color. By definition, zinc is not a transition metal. Zinc 2+ is D10, which is a filled D shell, and so most compounds of zinc are white or a very pale yellow. This is because we'll see later in the next module, module 4, about the electronic structure and how the colors of transition metals arise. So you can see here that zinc 2+ has 10 d electrons, which means that it has a full valence, which means it is not really a transition metal. So you can see some others like copper 1 it's also got a full D shell. Some common compounds, so copper sulfate, of course, which I just mentioned. This is a very nice blue color. Iron oxide, this orangey color, which you might be famous, which is quite famous. We know about iron oxide, especially hydrated iron oxide, is quite a bane in construction and anything that involves metal, and well, steel and whatnot. So copper iodide, and here Prussian blue is a dye. Nickel chloride, potassium technesate, sodium molybdate, and iron pentacarbonyl. So some of these, like for example, iron pentacarbonyl, as we'll see later, the carbonyl ligand is neutral ligand. So this is actually an iron 0 complex. It doesn't have an oxidation state like in the technesate. Here, this TC, this metal has actually got a +7 oxidation state there. Prussian blue, we have both positively charged and negatively charged ions here for iron. So the iron outside is positively charged, the iron inside is negatively charged, but we'll learn how to account for that as we go through. So there you go. So here are the oxidation states for the various different ions, cations involved. So as I said, the Prussian blue, the 2 different oxidation states for the iron, we had iron 3+ on the outside and iron 2+ on the inside. And then we have nickel chloride. So chloride is typically -1 in its most common oxidation state. And so it's going to be nickel 2+ here. Technetium I said was 7, and you can go through and see others like iron 0 in this iron pentacarbonyl at the bottom, and then the d electrons involved there, just for your knowledge. So general trends across the transition series. So the effective nuclear charge, or ZF, increases across the series, but not as much or to as large an extent as for the p block. So the 3d orbitals are held close to the nucleus as compared to the 4s, and hence the increase in nuclear charge has a smaller effect on the most distant electrons than observed elsewhere in the periodic table. So because there are a lot of d orbitals around there, they're typically closer to the nucleus, and so the effect of those of the nucleus is felt greater over all of the orbitals. So what happens is that electronegativities gently increase as we across. There's not a big jump, like it doesn't increase rapidly across the series. These lie between that of calcium 1, and this increase is remarkably small. So you can see it here, the ionization energies for the different, well, I guess elements. So it's for the whole periodic table. We have here, see, there's a big jump from hydrogen to helium, and then lithium, and it generally increases the ionization energy as we go from the first across to the noble elements energy, because they're very stable. We've got a full valence, they don't really want to lose that. But the thing that we're talking about here is the transition metals. So we have here this kind of almost flat, steady increase, and these are for the D blocks in the periodic table. So Whenever we reach the D block, we stop seeing this dramatic increase as we go across. In the D block, it's quite gentle, quite a small increase as we go from one to the next. And that's ultimately why these different oxidation states are available, is because the ionization energies for different oxidation states are relatively comparable. So, we would have seen before in like other metals, like the group 1 or 2 metals, that the energy to remove electrons that were not in the favorable oxidation state. So, for example, removing 2 electrons from lithium or removing 2 electrons from sodium is very difficult because it's going to reduce the number of electrons in a valence orbital. That second oxidation anyway. But in the case of the D block, we're removing electrons from orbitals which are degenerate, and so, or largely degenerate, especially in the gaseous form. And that ultimately means that there's not really a big increase in energy as we go from one to another. Then the size of the atoms decreases, also relatively slowly, at least compared to maybe what we would expect for the S and P block. And so there's a small decrease across the period, but because the atomic outer S electrons are shielded by the 3D electrons, only a small increase in the effective charge actually occurs, and hence the contraction in size is much smaller than that observed for the S or P block elements. Generally, going down the groups, as a group is descended, the outer electrons are placed in a more distant shell. As a column is descended, the D electrons experience a smaller attractive force from the nucleus, so ionization energy increases. The ionic radius increases, the electronegativity decreases, and generally the electrons are considered to be more diffuse lower in the table, so generally softer. And that's typically what we kind of expect with other regions of the periodic table as well, like the S and P block. Generally, as we go down the periodic table, we get more diffuse in terms of the ions. The melting points vary across the period. Generally, the increase, and then there's a contraction around manganese, and then it increases again, and these are relatively similar. We get, like, for example, soft materials here, like potassium, calcium. Generally, the softer it is, the lower its melting point. So notes on the elements in particular. So scandium is very, very rare. It generally only forms 3+ salts. There's not an awful lot of chemistry done with it because it doesn't really, or at least modern research done with it because it doesn't really do very much. It doesn't really access those other oxidation states. And if you think about it, it kind of makes sense because it has 3 electrons. So removing one of them makes it similar to a group 2 element. So it's removing 1 electron from the D3 makes it D2, which would leave it with only needing really 2 to be removed in order for it to get to a full valence, like its nearest noble element. And so it generally wants to remove all 3 electrons. There's not really a lot of energy gain just having the 1 electron or the 2 electrons remaining. And certainly not a lot of energy gain to be had removing just 2 electrons. Titanium, very light material, resistant to corrosion, dilute acid, so it's used in turbines, aircraft, and marine applications. It's relatively abundant. There's 0.6% of the Earth's crust, so certainly enough to be used in like a lot of applications. It's prepared from the mineral rutile, TiO2, by heating it up with carbon in chlorine to give titanium chloride, which is a liquid, and then this is reduced with magnesium. So you mine this titanium oxide. Vanadium is resistant to corrosion, dilute acids again, but not commonly used as its elemental form. It's used generally as a component in alloys, so it occurs in Venezuelan oil deposits, so extracted from flues following combustion, as well as a number of oxides in mineral forms. Purification is difficult because the higher oxides are reduced with carbon, aluminium, or iron sulfide. Chromium again, so generally also resistant to dilute acids, forms a lustrous surface. Typically, we like to electrolyte this in form of chrome. This was very common, I guess, back in the sort of 50s for cars and stuff. Like there's a lot of chrome going on then. That was, I suppose, the height of chromium electroplating. And it is now, I suppose, mostly used as an additive to form stainless steel. Obtained mainly as the ore chromite, so it's mined out of the ground with this iron with chromate as the anion. Purified by reduction with carbon. So the pure form obtained through, though by oxidation with oxygen in molten sodium hydroxide and the extraction in water as sodium chromate. Manganese, not a lot to say about it. It's an additive to steel, increases hardness. It's the third most common transition metal after iron and titanium, and it's purified by coke reduction. Iron is very, very common. There's a lot of iron in the Earth's crust. It's very accessible. It's very widely used as well. It's used in, just used as iron. It's also used as steel. It's present in biological functions. Reactive to form oxygen, especially in water, corrosion, but it's kind of reactive. Like it's very useful because it's very common, but it's also got its downsides where it reacts easily with oxygen and water to rust. So we have to protect it in some way. One of the ways that they used to protect it was with that chromium electroplating, and then they found they could alloy it with the iron directly, and that would form steel, and steel was much more resistant to corrosion. It's purified again by reduction with carbon. So you just add coke in some form. It's a magnetic element. It's an essential biological element, so it's present in hemoglobin, ferritin, etc. So there's iron deficiency is quite a bad problem. Cobalt, nickel, and copper tend to occur together in small quantities, generally as arsenides and sulfides. So typically these are together. Typically they're also reactive in similar manners, and so they're generally quite hard to separate from each other, although it is possible. Cobalt, not widely used in its elemental form, but oxides provide blue pigments, slightly reactive to acids, and generally less reactive than iron. It's a vital element as it appears at the center of vitamin B12, and it is a magnetic element. Nickel, then used in a wide range of alloys. So for example, cheap jewelry, it kind of has a luster which is not reminiscent of silver, resistant to attack by air, but take care, finely divided metal powder is pyrophoric. So it generally forms like if you increase the surface area, you increase the amount of or the probability of having a reaction with oxygen in the air. It's purified by conversion to the oxide and then further reduction with carbon. And again, magnetic element, copper, widely used metal, present in many alloys, brass and bronze, etc. Used for electrical wiring, used for some water pipes, although that's kind of being replaced by like PVC piping, because PVC piping is cheaper and copper is actually becoming very expensive. But copper is still widely used for transporting hot water, because it's more resistant to the changes in temperature. It has a high electrical conductivity, hence its use as in electrical wiring. And the first element of the coinage metals, so it's the copper, silver, and gold. Groups 8, 9, and 10 are described as the noble metals, since they are generally considered to be less reactive and less likely to form higher oxidation states. So effective nuclear charge as the first transition. So these are the general horizontal trends of the D blocks. As the first transition series, scandium to copper is traversed, one proton is added for each atom. So as Z increases by 1, as is 1 electron. Because the electrons in d orbitals are fairly close to the nucleus, they're quite good at screening out other electrons from nuclear charge. So like, for example, like 4s electrons or whatever. So ZF does not increase, or does increase, sorry, from left to right, but only gradually. Contrast this with the P block large increase in the effective nuclear charge from left to right. Has consequences for radii, ionization energies, and electronegativities. We saw that graphically earlier, where the radii generally decreases slightly as we go across the periodic table, because you're adding more and more electrons to the same shell. And so the distance and the shielding that they're experiencing from the nucleus is not changing. but their attraction based on how many electrons there are is increasing. However, because the gentle increase in the effective nuclear charge, the chemistry is less diverse going left to right than in the p block. So in the p block, obviously, there's a big difference, for example, between the chemistry of boron, between the chemistry of carbon, between the chemistry of fluorine. So metallic, i.e. atomic radius, so overall small decrease from left to right due to the gently increasing Z effective nuclear charge. So as we increase the effective nuclear charge felt by those d electrons, they're being pulled closer towards the nucleus. They're being pulled closer towards the nucleus, which means that they're contracting. And so you can see that here. So the row number 1, general decrease, row number 2, general decrease, row number 3, general decrease as well. Ionization energy is expected, is of course opposite of the radius. Overall small increase from left to right, decrease bottom to top. So it gets easier typically to remove the electrons as you go from the top to the bottom. And then there's an overall small increase from left to right. So group 4 to group 10, generally trend is increase, although of course there are spikes, and those spikes correspond to changes in the electron configuration. So if you sort of do out the d electron configuration of like manganese, iron, and copper, compare them to each other, you'll see why that trend might occur. You might be led on to a curious problem. So electronegativity, so this is the power of an element to attract electrons to itself when it is part of a compound. So generally follows ionization energy trend and overall gently increases left to right. So here is the D block. We see the increasing electronegativity as we go from left to right, which corresponds to a decreasing enthalpy of hydration of the cation. So the energy of the hydration, so the forming the water complex decreases. So the reaction with water is less extreme on this side. Like for example, copper and zinc is much lower than scandium and titanium whenever they are being hydrated. Going down the periods then, so increasing the enthalpy of hydration of cation goes down, decreases. So the energy given out whenever we dissolve it in water decreases, but we have an increasing electronegativity here as well. So they become somewhat more electronegative. So we can see the Pauling electronegativity from scandium to copper increases slightly. Less electropositive on the right-hand side, the bonding side, more reactive on the scandium side than it is on the copper side. So generally more reactive on the left-hand side than the right-hand side, and that's generally because the ionic nature changes. So the chemical consequences of some of these horizontal trends. So the trends have an effect on what coordination numbers are accessible, how they will bond, how they will form complexes, how useful those complexes are. So the coordination numbers, so most common coordination number in D block is a 6, so that's octahedral. So for example, we have hexa-aqua complexes. So for example, some metal is coordinated by 6 waters, that forms an octahedral complex. Typically, so for example, we could have hydrated iron, it's not uncommon. It's going to be coordinated by, in an octahedral fashion, to 6 waters, one on the end of each of these lines, much like that. So with the oxygen from the water pointing towards. And most likely it's an iron 2+ or something, or iron 2+ or iron 3+. Those are the most common oxidation states of iron. So greater than 6 is rare, but does occur, especially on the left-hand side of the D block. So for example, titanium can form a coordination. This is the titanium, which has a coordination number of 8. So it's got this diarsenide bidentate ligand. We'll talk about ligands towards the end of of this lecture. But basically, the ability to form 2 bonds with the metal center. So those 2 bonds are formed here and here, and then we also have 4 bonds to chlorines. So we have a coordination number of 8. Coordination number is just the number of bonds that are made to the central metal. Here we've got 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. We also have zirconium fluoride, which also has a coordination number of 8. So both of these are cubic. So you can see that the dashed red line here indicates a cubic structure. And then this would be a coordination number of 8. We also have some coordination number 7. So for example, this vanadium heptacyanonite. We have here an oxidation state of +5 on the vanadium. We have a pentagonal bipyramidal. So here's the structure here. So it's got a pentagon base, and then there's 2 pyramids above and below. So in order to form these high coordination numbers, typically the ligand is quite small and compact, because if it's very big, it's generally not going to leave enough space for all of the ligands to actually attach. So that's not the case here, where it's quite easy for these different ligands to attach. So D block high coordination numbers. So high coordination numbers are possible due to larger radius of the metal ion, leading to less steric repulsion between the ligands. Also greater chance of high coordination numbers if the ligands are small, so hydride, fluoride, and cyanide. So that's just what I mentioned a moment ago. If we have small ligands, they easily fit around. So small ions don't leave a lot of space for other things to fit around them, whereas large ions leave a lot of space. Conversely, if you do have a small ion, if you have small enough ligands, like some of these, hydride, fluoride, cyanide, they can still fit around in adequate numbers to perform these high coordination numbers. So a lot of this is just sterics, like kind of all fit around my metal center. And if it can't fit, then it's not going to feel full of attraction enough to actually stick around. So oxidation state, so increasing numbers of valence electrons from left to right. The highest available oxidation state also increases from left to right. So scandium to manganese, highest oxidation state is equal to the group number. So scandium chloride, titanium chloride, vanadium oxide, chromium perchlorate, and manganese peroxide. This is what's like permanganate ion, anion. So in each one of these, the metals have lost their all their d electrons. So from scandium to manganese, manganese is about 4 or 5 across. They can lose up to, or sorry, it's all the way across to 7. So manganese is D7 in its elemental form. It loses all of its electrons to form the permanganate ion. But the increasing ionization energies from left to right decrease the highest available oxidation state after chromium manganese. So for example, the fluoride's in the highest oxidation state for each of these. So scandium fluoride, so that's +3, titanium fluoride +4, vanadium fluoride +5. It's +5 because we have 5 fluorides, and each fluoride is -1. So -1 times 5 is -5. And then this is neutral, so it must be +5. Chromium fluoride is 6 and +6. Manganese fluoride is +4. Iron fluoride +3. Copper or cobalt fluoride +3. Nickel fluoride +2. And copper fluoride +2. So from iron to copper, the group oxidation states are not observed. Also, the +4, +5, +6 oxidation states get less common, i.e. they're less stable. So this is what leads to the pyramid distribution of common oxidation states for the first row of transition metals. That's what we saw earlier at the very beginning, where we discussed what common oxidation states were available. And typically they were the +2 to +3 oxidation states, except for things like vanadium, which commonly got access to its +5, chromium, which got access to +6. Chromic acid is chromium +6. Chromium +6 is incredibly toxic to humans, but chromic acid is still a very important industrial acid. Here's this pyramid again. So after we've discussed those different ionization energies, those different effective nuclear charge trends, let's have a look at the pyramid once again. So here we have the some of the elements from the first row of the transition metal series. We left out scandium because it's not really that exciting in terms of our trends or our reactivity. So we start with titanium and we go across to copper. We also left out zinc. So the accessible oxidation states are given the tick, and then the most common oxidation states are given a circle. So you can see that the oxidation states available increase up to manganese, and then after manganese, they decrease again. It's generally due to the stability of the D metal on losing extra electrons. So like, for example, in the case of iron, whenever it has a +6 oxidation state, it's not terribly happy with that, and so the energy required to keep removing those electrons gets more and more, which is why it's not really observed, like for example a +7 or +8, even though it is technically possible because it does have those electrons. And in the case of cobalt, it generally decreases just because of a reduction in that stability. Covalency then, so of course electronegativity, as we saw, increases going from left to right. So for example, scandium has a very low electronegativity, whereas on the right hand side, the things like copper has quite a high electronegativity. So this has a sort of a consequence on how they bond with other materials. So if the electronegativity increases left to right, the kind of bonds that scandium and copper form with other compounds, other molecules, other ions are going to be different. So scandium is typically going to form more ionic interactions and copper more covalent interactions, because copper, being more electronegative, is more capable of sharing electrons rather than have total electron transfer. So bonding here is more covalent, less ionic from left to right. So on the right hand side, kind of covalent bonding, sharing of electrons. On the left hand side, we have more ion. So scandium almost behaves just like a group 1 or group 2 metal. And the metals become softer acids left to right. So they become softer, larger, more diffuse. They interact better with, like, for example, sulfur rather than oxygen on the right hand side. So hard soft acid base theory was covered in earlier lectures and also in earlier topic videos. So the vertical trends, so how do the radii change? So typically we have triads because we have 3 rows of D block metals. So the radius increases from top to the bottom. Makes sense because we're adding 3 to 4, and then a smaller increase from 4 to 5. And the reason for that sort of large increase from 3 to 4, so here we've got a 0.12 angstrom increase, a 0.02 increase from palladium to platinum. The large increase here is brought about because of the f orbitals being added. Because the f orbitals first appear in the 4th shell when n is equal to 4 in our quantum number. Four to 5, we just add more, so there's not really that same large increase. Exceptions, of course, do exist. It's always the case in chemistry. Sometimes there is a small decrease in the contraction, or in the radii. So on the left-hand side, the 3rd row is actually slightly smaller than the 2nd row. So for example, here, titanium, 1.47 angstrom, zirconium, 1.60, and hafnium, 1.59 angstrom. So it's a slight decrease. So it's not always true that the 2nd and the 3rd, the 2nd is smaller than the 3rd. But basically the trend here is that the 1st row, so the 3D, is always going to be significantly smaller than the 4D and 5D. The 4D and the 5D are typically quite similar in size, but the 3D is much smaller. This unexpected reduction in the radius is called the lanthanide contraction, and it's due to the presence of 14 lanthanide elements between the second and third rows. The f orbitals are poor at shielding nuclear charge. So coordination numbers can be higher for second and third rows than the first. This ultimately comes down to, again, increasing size. So the coordination numbers for the second and third row are larger. Typically, they have access to greater numbers of bonds to the ligands. They're bigger. There's more space around them, especially if the ligands are small, like fluorides or cyanides or hydrides. You can fit a lot of those around the metal center. Then crystal field effects. Due to the increasing d orbital size, crystal field effects are more important for the second and third rows. Crystal field theory we will cover in the next module, but that's just another vertical trend, and it would be bad not to mention it now. Ionization energy. So first ionization energy normally increases down a group and get larger. So this is different to the S block metal. So first ionization energy here for nickel is 737, and then palladium 804, and platinum 865. But the sum of the first four ionization energies decreases, as we can see here. So the sums decrease as we would expect, but the first ionization energy actually increases as we go down the periodic table. So the decreasing sum of the first four ionization energies correlates well with the oxidation state stabilities. So nickel has the sum of the first four ionization energies of nickel is higher than that of palladium or platinum. And that also corresponds to the fact that nickel 4 is quite rare. It's quite hard to remove all of these electrons. So it's quite rare that we form nickel 4. Palladium 4, some are known because, well, the energy is lower, and then platinum 4 is fairly common. Platinum 4 is the basis for some important biological complexes. So generally what we see is that the higher oxidation states become more stable as the triad is descended, because it's easier to remove those electrons. They have a lower effective nuclear charge. It's easier to remove them. Even if the first one is more difficult, overall, all of them, it's easier. So again, we have a peaked distribution of oxidation states across the second and third rows, but shifted to higher oxidation states relative to the first row. And this is because of the sum of the oxidation states being lower. So the sum of the energies of the ionization energies. So again, we still have a peak, but now we have a generally higher, most common oxidations, because the energy of removing like one of the electrons versus like 3 or 4 of them is not that significantly large. And so generally so this is something I mentioned earlier. The first row has the most different chemistry of the 3 in the triad. So generally the chemistry of the second and third row of the D blocks is pretty similar. Like they have relatively similar chemistry. They do relatively similar reactions. They have relatively similar coordination states, coordination numbers, things like that. Whereas the first is usually the most significantly different. And it's mostly because of adding those F orbitals. So going from the first row to the second row, you add 7 F orbitals. But then the second to the third, you just have the same you just have F orbitals. You're not adding a new class of orbital. Okay, so in part 1 there, we talked about what is a transition metal. We talked about the oxidation states. We talked about counting d electrons, general trends, so electronegativity, atomic radius, and ionization energy. And we looked at the introduction to the first row elements.